day, students. Today we are going to learn about the interference of light. Now, first, let us see what light is. Light is essentially a transverse wave. Now, what is a transverse wave? Transverse wave is a wave that propagates through a medium. And while it propagates through the medium, it will form crests and troughs. Now, in the image shown here on the left side, we can see drops of water falling into the ocean. So when you have a disturbance on the ocean, the disturbance is the droplet falling on the ocean, and the medium, continuous medium, is the ocean. So when a droplet falls upon the surface of the ocean, disturbances are created upon the surface and it propagates as waves, forming crests and troughs. And these regions that bulge out are called the crests, and the regions that bulge in are called the troughs. Okay. So essentially, light is a transverse wave and it propagates through the medium as shown here in this animated video. Now, the distance between two consecutive crests or two consecutive troughs is called the wavelength of the wave. Or in other terms, we can define wavelength as the distance between a consecutive crest and trough. That is also the wavelength of the wave. Now, another parameter used to define the wave is its frequency. It is defined as the number of cycles per second passing through unit area. Okay. So, while defining light, these are just the essentials, but we can give a definition, exact definition, which is as shown on the right side as light is a harmonic electromagnetic wave consisting of periodically varying electric and magnetic fields oscillating at right angles to each other and also to the direction of propagation. This is shown in the next animation. So this is the actual image that can describe light as an electromagnetic wave. It has electric vectors shown in the blue vector and magnetic vectors shown in the red vector, and it is periodically varying. Okay, both these vectors are aligned perpendicular to each other, that is at right angles, and both these vectors are perpendicular to the x-axis, that is the direction of propagation. Usually we represent light in its electric vector. This is because we have the relation E by B is equal to velocity of light c in vacuum. That means electric vector E is equal to c times than that of the magnetic vector B. So comparing the electric vector and B vector, we can see that electric vector is far much greater than the magnetic vectors. Hence, we represent it using the electric vector E. And mathematically, it is given as an amplitude E0 into a harmonic function sine. Okay, so this is the mathematical representation. E is equal to E0 sine of kz minus omega t, where k is the propagation vector or propagation constant given by 2 pi by lambda wavelength, and omega is the angular frequency given by 2 pi nu, where nu is the frequency of the wave. Now let us see some of the properties of light. Light can reflect as shown here. The lotus upon the water, we can also see the reflection of the lotus on the water surface. Light can refract. See, when light passes through a glass block, it bends inside the glass block. That is, when it enters into the glass block, it bends. Again, when it is exiting the glass block, it bends. So when it travels from one medium to another medium, it will bend. Light can disperse, that is, it can separate into its component wavelengths. Here, when white light is passed through a prism, it will separate into its component VIBGYOR colors. So dependent upon the source, we get the corresponding spectrum. Light can produce interference. That is the property that we will be dealing in this chapter. See, here we can see the pattern of Newton's rings, the alternate bright and dark fringes produced in this manner. And this is an interference pattern. In nature, we can see these patterns on soap bubbles or on oil films spread on the road and all. Okay. Light can also produce diffraction. Now, what is diffraction? The bending of light near opaque objects. So here in the image shown, we see the sun on the slope of a hill. So we don't expect to see the rays from the sun below the tree tops, but here we can see that there is a glare, or there is some light penetrating into the below the trees. So that is because light is bending from the hilltop surface. And this is an example for diffraction of light. Light can scatter. Okay, so in this image shown, we see both the diffraction property and the scattering property of light. So when light passes through the atmosphere, it falls upon many dust particles and cloud droplets, and it bends away from its path. So when it is diffracting through the atmosphere, light undergoes a lot of scattering. It sees a lot of particles and it scatters from one point to another. It undergoes a lot of scattering. And in the scattering process, the longer wavelengths get lost, and we get only the shorter wavelengths of the sun. And that is why we see the sky as blue. Okay. But if we look at the sun, okay, when we look at the sun through the horizon, light travels very large distances, comparatively large distances, where other than when light is just right above our heads. So when light travels larger distances, the scattering effects become smaller and diffraction effects become prominent. So when scattering effects become smaller, the smaller wavelength in the light gets lost and the larger wavelengths in light become prominent. And that is why we see the purple or reddish hues of sun during sunset and sunrise. And another property of light is that light can become polarized. This image shows the linear polarization of light. Okay. Now, what is interference of light? When two light waves, they coincide upon each other, what happens is they superimpose upon one another to produce a resultant wave. And this is explained by the principle of superposition. The principle of superposition states that when two or more waves pass simultaneously through a medium, they superimpose upon one another to produce a resultant wave. And the resultant displacement at any point and at any instant is the vector sum of the individual displacements. Okay. Now, if we consider two or more waves, let us have a wave y1, another wave y2, another wave y3, another wave y4, another wave y5, another wave y6, let it all happen to coincide upon each other. Then we get a resultant wave given mathematically as y1 plus y2 plus y3 plus y4 plus y5 plus y6. And if we have n number of waves, the vectorial sum of all these waves give the resultant displacement of the resultant wave. Now, let us mathematically derive what is the displacement of. Now, in nature, we see these interference phenomena, but to study it, we need to see the mathematical side of it. So let us first mathematically calculate what is happening when we find the vectorial sum of different waves. So for that, let us consider the superposition of two light waves. We are going to define two light waves as y1 given as a1 sine of kx minus omega t plus phi 1. Okay. So we are assuming that light is propagating in the x direction and it is having an amplitude of a1 and phase phi 1. Okay. Now another wave happens to superimpose upon it, and the second wave is taken as y2 is equal to a2 sine of kx minus omega t plus phi 2. This wave is also propagating in the x-axis, but it has a different amplitude a2 and different phase phi 2. Okay. So if they interfere upon each other, they will follow the principle of superposition. Hence, the resultant vector is given as y is equal to y1 plus y2. And this can be written as a1 sine of kx minus omega t plus phi 1 plus a2 sine of kx minus omega t plus phi 2. Okay. Now here we can look into the sine term as sine of a plus b, and we have this trigonometric relation. Sine of a plus b is equal to sine a cos b plus cos a sine b, right? Hence, this expression can be expanded as a1. I'm going to read this as a and this as b. Okay, fine. Hence, I can write a1 sine kx minus omega t cos phi 1 plus cos kx minus omega t sine phi 1, right? Plus a2, we expand in the similar manner, sine of kx minus omega t cos phi 2 plus cos of kx minus omega t sine phi 2. Now in this expansion we can see that we have similar terms of sine kx minus omega t and cos kx minus omega t. So taking those terms together, sine of kx minus omega t into the remaining term will be a1 cos phi 1 plus a2 cos phi 2, right? Now the next term plus cos of kx minus omega t, common term will be a1 sine phi 1 plus a2 sine phi 2, right? Now, since we consider the superposition of two light waves, we got these two terms here, a1 cos phi 1 plus a2 cos phi 2 and a1 sine phi 1 plus a2 sine phi 2. If we consider the superposition of three light waves, we get an additional term here, right? And here. And if we consider the superposition of n light waves, we will have additional terms here and here. Okay. So I'm going to generalize that term. Okay. Generalizing, we get A1 cos phi 1 plus A2 cos phi 2. It is written as generalized term A cos phi. Let this be equation 1. And A1 sin phi 1 plus A2 sin phi 2 is equal to A sin phi. Let this be your second equation. Okay. So substituting in these terms, I can write sine of kx minus omega t A cos phi plus cos of kx minus omega t A sin phi. Okay, so the common term will be A. Remaining I have sin kx minus omega t cos phi plus cos kx minus omega t sin phi. That can again be reduced as sine of A plus B form, that is kx minus omega t plus phi. So this is the resultant wave. This is the expression for the resultant wave, where A is the resultant amplitude and phi is the resultant phase. Let this be equation 3. Now, we only have the individual amplitudes and the individual phases, okay? We don't have the resultant amplitude and the resultant phase. So in order to calculate that, what we do is, we take the sum of the squares of the first and second equation. The sum of the squares of the first and second equation gives us a square cos square phi plus a square sin square phi. That is, we are taking the sum of squares on the right hand side and written it together, okay? And on the left hand side, what we get is a1 cos phi 1 plus a2 cos phi 2 the whole square plus a1 sin phi 1 plus a2 sin phi 2 the whole square. Okay. Now here this becomes a square into sin square phi plus cos square phi, that is 1. Okay. So I can write a square is equal to, expanding the other terms on the right side, I get a1 square cos square phi 1 plus a2 square cos square phi 2 plus 2 a1 a2 cos phi 1 cos phi 2 plus a1 square sin square phi 1 plus a2 square sin square phi 2 plus 2 a1 a2 sin phi 1 sin phi 2. Okay, so this becomes a square is equal to, I'm going to bring together terms of a1 square. So that becomes a1 square is equal to sin square phi 1 plus cos square phi 1. Okay, plus a2 square of sin square phi 2 plus cos square phi 2 plus 2 a1 a2 into sin phi 1 sin phi 2 plus cos phi 1 cos phi 2. Now we have the relation sine of or else we can write cos of, okay, so I'm going to write it here, cos of A minus B can be written as what? Cos A cos B plus sine A sine B. Okay, so we can use this relation here. Then this expression becomes A1 square into 1 plus A2 square into 1 plus 2A1 A2 cos of phi 1 minus phi 2. A square is equal to A1 square plus A2 square plus 2A1 A2 cos phi 1 minus phi 2. Now, we know that the intensity of a wave is directly proportional to its amplitude square. That is, intensity is proportional to the amplitude square. So from that inference, we can write this expression in terms of intensity. Okay, so I write the intensity of the resultant wave is equal to I1 plus I2 plus 2 square root of I1 into square root of I2 cos phi 1 minus phi 2. Okay, so let this be equation 4 and this be equation 5. Equation 4 is in terms of amplitude square and equation 5 is in terms of intensity of the wave. Hence, we get an expression for the amplitude of the wave A from equation 4. Now, in order to find the resultant phase of the wave, what we do is we find the fraction second equation by first equation, and this implies sine phi by cos phi, that is tan phi is equal to A1 sine phi 1 plus A2 sine phi 2 divided by A1 cos phi 1 plus A2 cos phi 2. Hence, the resultant phase phi can be written as tan inverse of A1 sine phi 1 plus A2 sine phi 2 divided by A1 cos phi 1 plus A2 cos phi 2. Let this be equation number 6. Okay, so here we have derived the expression for the resultant wave y is equal to A sine kx minus omega t plus phi, where the amplitude is given from expression 4 and the phase is given by expression 6. So let us write down the mathematical expression in a neat form. The resultant wave when two light waves superimpose upon each other is given as y is equal to A sine of kx minus omega t plus phi, where A is equal to A1 square plus A2 square plus 2A1 A2 cos of phi 1 minus phi 2 whole raised to 1 by 2. Okay, and phi is equal to tan inverse of A1 sine phi 1 plus A2 sine phi 2 divided by A1 cos phi 1 plus A2 cos phi 2. Now let us see some cases here. So the first case is what happens when the phase difference phi 1 minus phi 2 is an even integral multiple of pi. Even integral multiple of pi. Okay. Now when this happens, we have the amplitude to be a1 square plus a2 square plus 2a1 a2 cos of 2n pi. The cos 2n pi is 1. Hence we get a1 square plus a2 square plus 2a1 a2. We can see cos 2n pi to be 1 if just by substituting values for n. If n is 0, you have cos 0, that is 1. If n is 1, you have cos 2 pi, that is again 1. If n is 2, you have cos 4 pi, that is again 1. Okay. So generally when we have cos 2n pi, we have it to be equal to 1. So this expression becomes like this, whole raised to 1 by 2. That is a is equal to a1 plus a2 square whole raised to 1 by 2. So that cancels out. You get a1 plus a2. And if a1 is equal to a2, you get the maximum amplitude. If a1 is equal to a2 is equal to a, you get the maximum amplitude to a. And this condition is called the constructive interference of light. Okay. Now the second condition, if the phase difference is an odd integral multiple of pi, that is phi 1 minus phi 2 is an odd integer represented as this term, odd integral multiple of pi. So we get amplitude to be a1 square plus a2 square plus 2a1 a2 into cos of this term. If we get n is equal to 0, I have cos pi, that is minus 1. When n is equal to 1, I have cos 3 pi, that is also minus 1. When n is equal to 2, I have cos of 5 pi, that is also minus 1. So I have into minus 1, right? Generally, I have this term into minus 1 whole raised to 1 by 2. And this is a1 minus a2 the whole square raised to 1 by 2. It cancels out and I get a1 minus a2. Now if a1 is equal to a2 is equal to a, I get the least possible value for amplitude, that is 0. And this condition is called the destructive interference of light. Okay. Now in terms of the intensities of light, how can I write it? Here, intensity max will be the square of the amplitude. That is, I get 4 times a square, that is 4 times I. Now, for destructive interference, I get the intensity, least possible intensity. So I can write I minimum is equal to the square, that is 0. Okay. Now, the expression for intensity, general expression for intensity was given as I1 plus I2 plus 2 root of I1 I2 cos of phi 1 minus phi 2 whole raised to 1 by 2. Okay. So for constructive interference, here I will have the expression I is equal to what? I1 plus I2 plus 2 root of I1 I2. And for destructive interference, I will have the expression of intensity as I1 plus I2 minus 2 root of I1, I2. Now, pictorially, let us see what is constructive interference. Now I have the yellow dots showing the displacement at a particular point, and the resultant is shown here. So for each point, the resultant is plotted in the right side. Okay. Now if we map that points, we get a wave having twice the amplitude of the individual waves. And here you should see that the crest of the first wave matches the crest of the second wave. So the phase difference between the waves is 0. Okay, the phase difference here is 0. Or the phase difference can be an even integer. Okay. So it can be 0 or any integral multiple of an even integral multiple of pi. So hence, the constructive interference of two waves in phase is given as the resultant wave shown below. If the amplitudes of the individual waves are A, then the amplitude of the resultant wave will be 2A. Now in the next case, for destructive interference, here the trough meets the crest of the other wave, or the crest of one wave meets the trough of the other wave. So taking the resultant at each point, we can see all over the resultant wave, the displacement will be 0. So here, the interference of two waves in antiphase. See, the phase difference between them is either pi or an odd integral multiple of pi. The phase difference between these two waves is either pi or 3 pi, 5 pi, 7 pi, 9 pi, like that. So if these two waves interfere, the resultant wave is as shown below. Okay, and if the individual amplitudes is A, then the resultant will have 0 amplitude. Okay, or a uniform light. That's all that we can say. There is no pattern observed. There is just a uniform light. That's all for today. Thank you.